Okay, welcome everyone. Today we are happy to have Zimet, who's going to tell us about K3 metrics.
Okay. Are you able to share your slides, Max?
Yeah,
I did see it a second ago. Okay, here we go.
There was some weird bug where I quit my email program in order to, yeah, and then somehow it quit the Zoom call. Anyways.
All right, don't worry about it. We'll overcome everything.
Yeah. All right. It's good to be here.
Finally.
Thank you for the invitation.
All right, thanks for joining us.
Okay, shall I get started? Okay. You can hear me, right? The Zoom audio is on. Okay, good. Okay, so I'm gonna be telling you about recent work on K3 metrics. So let me just go ahead and get started. Okay, so let me just review the motivation for why string theorists might be interested in this. Then I'll also give a quick intro for mathematicians. So Calabi-Yau compactification has played a central role in string theory because if you compactify the perturbative superstrings or M theory or F theory on them, then you get lower energy vacua with lower dimensional vacua with low energy supersymmetry. So type 2 compactifications preserve 4D n equals 2 supersymmetry and are the natural setting for mirror symmetry. And then heterotic and orientifold compactifications preserve 4D n equals 1 and have been used for string phenomenology. More generally, Calabi-Yau compactification is very interesting because it's the setting in which much of our understanding of non-perturbative string theory has been developed. So K3 has played a particularly important role because it's in a sense the simplest compact non-toroidal Calabi-Yau manifold. And because of this accidental isomorphism, it's not just Calabi-Yau, it's hyper-Kahler, because in 2 complex dimensions, SU2 is the same as SP1, so any Calabi-Yau manifold will be hyper-Kahler. And so that's maybe one way of understanding why the only compact examples in 2 complex dimensions are K3 and T4. So K3 is also, yeah, okay. And a concrete way to think about K3, which will be useful throughout this talk, is as an orbifold of a torus, which you then resolve the fixed points of the action. And because K3 is hyper-Kahler, it preserves even more supersymmetry than a typical Calabi-Yau manifold. So, if you want to build a threefold out of it, you multiply it with a torus, and you get a vacuum of 4D n equals 4 supersymmetry, not just 4D n equals 2. And because this preserves the same number of supercharges as heterotic string theory on a torus, that suggests this natural duality. And this has played an essential role in our understanding of how the various superstrings are related. And K3 string compactifications also were the earliest example where black hole microstate counting in string theory. Okay, so I just told you a huge number of successes. I told you that K3 has been investigated by string theorists for decades now, and yet the most basic data that you need in order to formulate a string vacuum, namely the metric, has not been known to us. So one of the first things you see in a string theory class is the nonlinear sigma model action. And we're supposed to obtain tree-level string vacua from conformal field theories, such as the nonlinear sigma model. But in reality, we don't have the metric, and so the starting point needed to formulate this CFT is not present. So this question is particularly well motivated for K3 as opposed to other Calabi-Yaus, because the beta function of that nonlinear sigma model is exactly 0, not just at leading order in alpha prime because of how much supersymmetry we have. As an example of our ignorance, even for K3, almost everywhere in moduli space, the world sheet partition function is not known. So more generally, there are huge swaths of questions that one might ask of UV complete string theory compactified on K3 that are just inaccessible without the metric. So I'm going to describe for you today some recent work with Zimet and Arnav, where we have two constructions of K3 metrics. One of them I'll call the Higgs branch construction is completely explicit, and then the other one is as you see, it's missing some discrete data. So which one way to think about them is certain open string Gromov-Witten invariants. But by comparing these two formalisms, then we can read off those invariants and we expect to be able to make that second construction also completely explicit. Yeah, let me I'll say more about that throughout this talk. Okay, so now let me give an introduction for the math audience. So I told you we're going to have two constructions. One is the Higgs branch construction. So the idea here will be to construct K3 as the hyper-Kahler quotient of an infinite dimensional affine space. Concretely, there will be 3 moment maps, and we'll study the vanishing locus of those moment maps in this infinite dimensional space. And then we'll quotient by some infinite dimensional Banach-Lie group, and that will give a K3 surface. There's one such construction corresponding to each torus orbifold limit in the moduli space of Ricci-flat K3 metrics. And in principle, we expect that each of these constructions will cover the entire moduli space of K3 metrics, but they'll be particularly useful near their corresponding orbifold limit, because then in that limit, there's a perturbative formalism one can use in order to explicitly describe the solution of this hyper-Kahler quotient. Yeah, okay. The one way to, what the moment maps are is they're just roughly they're the anti-self-duality equations on the dual torus to this torus. The intuitive way to think about what this moduli space is that K3 is the moduli space of singular equivariant instantons on the dual torus. So I'll explain that more later. But let me just give some intuition for why you might have expected something like this. First of all, we know from Mackay that one can construct K3 as a moduli space of certain sheaves on K3 itself. And we know also from the derived Mackay correspondence that there's a correspondence between sheaves on K3 and equivariant sheaves on a torus, which you can orbifold in order to get K3. So by putting those two things together, one learns that K3 ought to arise as a moduli space of certain equivariant sheaves on a torus. And then so from there, it's just a little bit, it's not too surprising that one can obtain this moduli space of sheaves as certain singular solutions of the anti-self-duality equations. Okay, I'll make that more explicit later. Let me just, because I mentioned this derived Mackay correspondence, let me reformulate that for physicists real quick. There's a familiar idea where a nonlinear sigma model on K3 is the exact same CFT as a torus orbifold deformed by certain twisted sector moduli which resolve the orbifold. And now if you think about d-branes in the string vacuum defined by that CFT, then you get two different descriptions of those d-branes. One is as certain d-branes wrapping an orbifold, and one is as d-branes wrapping a K3 surface. And so yeah, okay, that's the perturbative string theory intuition for this correspondence, but where there ought to be two different ways of describing moduli spaces of D branes wrapping different things. Okay, and like I said, this construction is completely explicit near the orbifold limit. Okay, and then I won't spend much time talking about this generalization, but there are analogous constructions that hold for if you dimensionally reduce the anti-self duality equations, you can get the Bohemolny equations on T3, or the Hitchin equations on T2, or the Nahm equations on a circle. This construction works in those cases as well. So you get, you know, ALF, ALG, or ALH manifolds. In particular, one learns that certain moduli spaces of singular Higgs bundles on a punctured sphere correspond with moduli spaces of singular equivariant Higgs bundles on the torus that you can orbifold and then, you know, deform to get that sphere. So I can say more about that if you want later, but yeah, for now I just wanted to mention that this construction works slightly, yeah, in more generality. Okay, and then the Coulomb branch construction. So this, there's a formula for K3 metrics in terms of certain K3 open string reduced Gromov-Witten invariants. So this should be thought of as the Strominger-Yau-Zaslow construction of a K3 surface at the level of the metric, not just the complex structure. So, you know, there's the Kinsevich-Soebelman paper where they say if you gave me some open string Gromov-Witten invariants of K3, I could, roughly speaking, I could construct the mirror as a complex manifold. So here it's the same idea, but doing so for including the metric. Instead, because we haven't yet managed to directly attack this counting problem, what we'll do is we'll compare the formulas produced by this approach with the formulas from the other approach in order to read off those open string Gromov-Witten invariants. So there's this amusing idea where you can use the Higgs branch approach to write down K3 metrics, then relate them to the formulas from the Coulomb branch approach to extract these open string Gromov-Witten invariants, and then those in turn specify a second construction of K3 metrics whose regime of validity overlaps with the Higgs branch approach, but it's different. So you get even more, you know, the regimes in which the two approaches are perturbatively useful is different, and so yeah, okay. And then via string dualities, we can reformulate this open string Gromov-Witten problem in a couple of different ways. Okay, this way is very familiar to mathematicians. This is just saying our open string Gromov-Witten invariants are going to be associated to holomorphic curves in K3 with boundary on some elliptic fiber. And so there's a tropical limit of that problem where it looks like you're just looking at little string webs on the base of an elliptically fibered K3 surface. So I'll call that the tropical limit. More non-trivially, we can relate these to generalized Donaldson-Thomas invariants of some auxiliary non-compact Calabi-Yau threefold. And then there are versions of these open string Gromov-Witten invariants and generalized Donaldson-Thomas invariants. There are different versions of those problems for K3 surfaces that arise as generalized Kummer varieties. Yeah, those problems might be particularly amenable to direct attack. Okay, so I'll say more about that later. Okay, so let me give a bit of background first on the Coulomb. Let me first introduce the Coulomb branch approach. The physical context for this approach is what's called a little string theory. So the idea is that heterotic string theory is some 10-dimensional theory. It has an SO32 gauge group, and so one can consider instantons in that theory. These are some, these describe some spatially varying field configuration in 4 of those 10 dimensions. If one considers a limit of these instantons where their size modulus shrinks down to 0 size, then it looks like a very singular configuration in that Yang-Mills theory. But nevertheless, in the full string theory, this is a perfectly sensible object, and we just think of it as a 5-brane living in the 6 transverse dimensions to that singularity. And from the supergravity perspective, there's a very interesting fact about this 5-brane, namely that if you take the string coupling of the heterotic string theory to 0, the bulk dynamics turns off because you've turned off the string coupling, but nevertheless the world volume of those 5 branes remains interacting. And from the supergravity perspective, this works because the soliton is extremely singular. So the dilaton is actually a dynamical field in string theory. And so even if you set the vacuum expectation value of the string coupling to 0 at infinity, the dilaton can diverge as you go down the throat towards the core of the soliton. And then little string theories are not quantum field theories. For example, they have T-duality. So there is no unique stress energy tensor because there's no unique way to say what geometry they're seeing. Okay, so in order to understand why where K3 enters into this problem, we're going to use some string dualities. So strong weak duality replaces a heterotic 5-brane by a D5 brane in type 1 string theory. So now if we want to study the moduli space of this 5-brane wrapping, let's say T2 first, then we can use T-duality twice to replace the D5 brane by a D3 brane. So then you end up in a type 2b orientifold on T2 mod D2. And the non-perturbative way to think about this string vacuum is as F theory on elliptically fibered K3 surface. So at generic points in moduli space, this T2 mod D2 gets resolved to a more general CP1, and so yeah, the more general way to think about this vacuum is F theory on K3. And our our heterotic 5-brane is just a D3 brane probing this configuration. So its moduli space is the CP1 of the base of that F3 compactification. Okay, and then we can use the exact same approach to study the moduli space of the little string theory compactified on T3. So now we just use T-duality 3 times to replace the D5 brane by a D2 brane. And now so we have type 2a orientifold on T3 mod Z2, but then there's an extra dimension of the moduli space provided by the M theory circle, which upgrades this to M theory on K3. So again, at generic points in the moduli, in the parameter space of this little string theory, the moduli space is smoothed out to a smooth K3 surface. Okay, and so this is what I was just saying. The moduli of the heterotic string theory, because we took G string to 0, are non-dynamical, and so they're just parameters of the little string theory. And similarly, the gauge symmetry in space-time just tends to a global symmetry of the little string theory. So heterotic string theory on T2 has some rank 20 gauge group, and so the little string theory on T2 will have a rank 20 global symmetry group. Okay, so now I can explain our approach for describing metrics in this approach. Namely, we studied the little string theory compactified on T2, and then we further compactify on a very large circle. So I call this S1R. The radius of that circle is R. And capital R is what's going to give us a perturbative parameter in order to describe this moduli space. So R goes to infinity. In that limit, we know what the geometry looks like. It's just the metric on the base of the F theory compactification, and then you have the flat metric on the torus fibers. So this is called the semi-flat limit, or sometimes the large complex structure limit. This metric is Ricci-flat, but it's singular at the 24 singular fibers. So the object of this construction is then to produce a corrected metric, which is exponentially close to this metric away from the singular fibers, but which gets large corrections near the singular fibers.
Wait, I thought you wanted K3 in type 2 string theory. Not in F theory. So why don't we go down further on more circles?
Yeah, good.
I mean, F theory doesn't see the fiber, right? The fiber just keeps the track of the complex structure. It doesn't see the volume of the fiber. So how are we going to get a metric on the entire K3 from only that?
That's right. So that's where compactifying on this extra circle comes from. So the moduli space, so the little string theory on T3 is dual to to M theory on K3, and M theory does see the whole K3 surface. So the R goes to infinity limit is where M theory limits to F theory, and so there the metric is the normal F theory metric. But away from R equals infinity, you see the whole K3 surface. So geometrically, what R goes to infinity is the volume of the fiber shrinks down to 0 size, and then as R goes away from infinity, the fibers fatten up. So
we want M theory on K3 probed by like an M2 brane?
Exactly.
So you want the metric that an M2 brane sees, or a metric that a fundamental string sees in type 2 string theory?
Yeah, yes. So in this picture, we have an M2 brane probing K3. That's the little string theory on T3 is dual to an M2 brane probing K3. So that's the metric that's the moduli space that we're after.
Okay.
And so, yeah, like you said, then the little string theory on T2, as that third circle gets very big, is going to limit to the F theory vacuum. And so in that limit, the volume of these fibers shrinks down. So in that limit, we know what the metric looks like, and then we're just going to study the corrections away from that limit.
And I guess compactifying further to type 2A doesn't really buy you anything in this case, right? There's no, so the M theory metric is just fine.
Exactly. Yeah, one could imagine trying to use this approach to then study, the B field on K3. That's the extra data that you need to formulate the type 2A vacuum. So that's an interesting question. Okay, so the corrections away from this R goes to infinity limit are provided by instantons in this little string theory. And those are obtained by taking the world line of some 4-dimensional BPS particle and wrapping them around this large circle. Okay, I need to have a way to distinguish between the
I'm sorry, I interrupted you, so now I forget what the limit was. Which limit?
Oh, the limit is R goes to infinity.
And that's so now remind me, R to infinity does what to the fiber? It shrinks it, right? Okay, yeah. That's so now we have a finite size fiber of size 1 over R, area 1 over R, right?
Exactly. Okay, I need a way to distinguish between the little string theory compactified on T2 and the little string theory compactified on T3. So I will call the first one the 4-dimensional theory and the second one the 3-dimensional theory, even though they're both 6-dimensional, just because I'll count the non-compact dimensions of the 5 brane. Okay, so with that in mind, the instantons that describe corrections to the semi-flat metric are just provided by 4-dimensional BPS particles wrapping this very large circle. So then the action of such an instanton is going to be the radius of that circle times the mass of that BPS particle, and so as long as the particles are massive, then their corrections to the metric will be exponentially suppressed at large r. And so the only time you'll get large corrections is if you have a massless particle, and those are precisely near the singular fibers, because strings that stretch from the D3 brane to the 7 branes at the singular fibers will be massless, and so you'll get very large corrections there.
And the 4-dimensional theory we're talking about here is little string theory on T2?
Exactly.
It's VPS.
And yeah, so the 4-dimensional theory you can think of as being dual to a D3 brane probing F theory on K3, and the 3-dimensional theory is dual to an M2 brane probing M theory on K3. So the 4-dimensional picture is useful for talking about BPS states, which provide these instantons, and the 3-dimensional picture is useful for seeing seeing the metric. That's the frame where you actually see the whole K3 surface. Okay, so this is just I'm going to give a very quick review of the formalism due to Gaito-Moore-Knightsky that we use in order to study the metric on this moduli space. So the idea is that physics provides certain canonical piecewise holomorphic functions on this moduli space, which are the expectation values of certain line operators wrapping this large circle. And because these observables are supersymmetric, they're holomorphic. So zeta here labels which complex structure we're talking about, because K3 has a whole CP1 of complex structures. So for each zeta, you get a locally holomorphic function on the moduli space, and K3 doesn't have globally holomorphic functions because it's compact. So the way one gets around that is that they're discontinuous at certain points, and those discontinuities are determined by a wall crossing formula. And so one then knows. So given the counts of those BPS states in the 4-dimensional theory, or the counts of those instantons in that affect the metric in the 3-dimensional theory, then one knows the discontinuities of these functions, and then that turns out. So furthermore, we know the large R limit, and we know the zeta goes to 0 limit. Those are certain nice limits. And so that turns out to be all of the data one needs to formulate a Riemann-Hilbert problem. So one has some piecewise holomorphic functions, one knows their asymptotics, and one knows where one knows what their discontinuities look like. And so that's the data of a Riemann-Hilbert problem. And then Gaito-Moore-Knightsky write down this integral equation which characterizes solutions to that Riemann-Hilbert problem. And then they prove that there exists a unique solution to that Riemann-Hilbert problem at large R. And the existence theorem is very concrete. It's not just an abstract existence theorem. You can actually construct the solution. Namely, we know this semi-flat limit of these functions, and so you plug that in on the right-hand side over here. Evaluate this right-hand side. That gives you a first-order approximation to these functions. Then you plug the first-order approximation in, and you get a second-order approximation, and you can keep iterating that. And at large enough R, that's going to converge and give you these functions.
So these are now directly coordinates on K3.
That's right.
And how do we know all these limits?
Yeah, good. So this limit comes from the fact that
sorry, which limit?
R, yeah, sorry, the semi-flat limit, the R goes to infinity limit. So in that limit, the one obtains these semi-flat coordinates, and that just comes from the fact that the physical characterization of what these functions are is their expectation values of some line operator wrapping that very large circle. And so in the limit where the size of that circle goes to infinity, the expectation value is just completely classical. And so one just writes down the action. So, so this line operator is some Wilson-Tooft line. So it describes some very heavy probe particle in the little string theory. And so this is just the action of that probe particle wrapping that large circle. This is just the classical action of that probe particle. So, Z gamma is the central charge of that particle. So this is roughly the mass of that particle. And then, yeah. So this is just the.
When you say you're describing the little string theory, are we talking about, should I think about like a, basically like type 1 D5, D9 system, like with a, I mean, essentially D5 brains, D9 brains, is that what we're doing? Or
yeah,
how do you,
one way to think about.
How do you know these particles? Like, what are these?
Yeah, good. So the charts, okay, let me say it this way. The 6-dimensional little string theory, first of all, it has a low energy description as some SU2 gauge theory with 16 fundamental hypermultiplets. And so we know it has particles in it. So we know it has 0 brains. It also, by virtue of being a little string theory, it has strings. So those strings wrapping some of the circles that we compactified the little string theory on will give more particles. And then furthermore, there are monopoles in that SU2 gauge theory. So those are some codimension 3 solitons. And so once we wrap on T3, then those will give some extra instantons that contribute. So we have 0 brains, 1 brains, and 2 brains, which all contribute instantons to this sum. So the charge lattice here, that describes the charge lattice of the little string theory, is just gonna, it contains all of those different types of charges.
At the end of the day, I just need enough coordinates to describe a 4-dimensional space.
That's right. Yeah. So this is a huge overcounting, and there are lots of relations between these functions. So indeed, one gets one of these functions for every point in this charge lattice, it's just that they're all related to each other. There are only 2 independent ones, one for the electric charge and one for the magnetic charge.
One can actually make this completely explicit.
Yeah, exactly. The charge lattice, is very nice. It's just Z2, the electric and magnetic charges, plus Z to the 20 for all of the flavor charges. And we know exactly, yeah, okay. So the only part of this that's not entirely explicit is we don't know what these integers are. So these are certain reduced Gromov-Witten invariants for K3. And again, one can think of that in the D3 brain picture as just string webs, which are stretching from the D3 brain to various 7 brains. Or T-dual, if you T-dualize a large transverse circle to all of that, then it's just, you get an M5 brain wrapping an elliptic fiber. That's what the D3 brain becomes. And the string webs become M2 brains wrapping some holomorphic curve in this M3 compactification and ending on that singular fiber, or sorry, ending on the elliptic fiber. So those are the holomorphic curves that are familiar from the Gross-Siebert program. Yeah, so yeah.
In particular, these are disk instantons, right?
I'm not positive
okay,
that only genus 0 will contribute.
I apologize. Could you repeat again this Gross-Siebert picture, just so I can remember, remind myself what this looked like? Yeah.
So the idea is that motivated by the Strominger-Yau-Zaslow idea of what mirror symmetry looks like. So let me just focus on what that is for K3. What that means is that if I have some D0 brane probing K3, so its moduli space is all of K3. That if I then T-dualize some elliptic fibers, that moduli space is the same as some D2 brane wrapping an elliptic fiber of the K3 surface. And the moduli space of the D0 brane is completely classical. It's just the K3 surface that it's seeing. But the moduli space of the D2 brane is it experiences quantum corrections due to open string instantons, world sheet instantons that end on the D2 brane. Yeah, normally one talks about disk instantons because those are the ones that affect the superpotential. But with this much supersymmetry, one is the quantity to look at is, instead of a superpotential, is the metric on the moduli space, and that can get corrected by higher genus instantons, not just genus 0. Does that answer your question, or?
Not entirely. So wait, you say you expect to have higher genus corrections too?
Yeah, that's right. Yeah, we know. So if one way to see this is if you study a limit where the D3 brane zooms in near one of the singular fibers, and you take a low energy limit, then you just get a 4-dimensional quantum field theory rather than the full little string theory. So if you just zoom in near one singular fiber, and we know the parts of the BPS spectra of those field theories. So for example, you can get the Minahan-Nemeshansky CFT from this approach if you zoom in near like a 4-star singular fiber, or 3-star or 2-star, from work of Knightsky and collaborators, we know that some of the holomorphic curves that contribute to that field theory spectrum do have higher genus. There might be some subtleties with whether one's talking about the Gromov-Witten,
I think we may be confusing something here. I mean, your construction should be parallel to constructions of such metrics for non-compact hyper-Kahler manifolds, like, for example, a Guri-Vafa metric, where its analogs, I think, are very well known. Certainly, I think in both math and physics, right?
Yeah, so
and there, I think it's only it's just the disk instantons that contribute, and the analogous, the wall crossing is that of which kinds of disks provide good coordinates and moduli.
Yeah, that's right. Actually, okay, I think I might be confusing things by saying, there's a question of whether one is talking about genus 0 on the world sheet or genus 0 in space-time, and what I'm trying to say is that they're higher genus in space-time. But from the world sheet point of view, we might still be talking about genus 0 invariants. Okay, so yeah, I think that's right. Okay, and then given these, so these functions, as Mina pointed out, they're highly redundant, but the electric and magnetic ones are independent coordinates, and they provide holomorphic Darboux coordinates on this manifold. In particular, the Laurent expansion of the Y's goes on for forever, but nevertheless, when you wedge these two combinations together, you get this very simple Laurent expansion just with these 3 terms. Omega plus, in the canonical zeta equals 0 complex structure, omega plus is the holomorphic 2 form and omega k is the Kahler form. So this 2 form omega of zeta encodes omega I, omega j, and omega k. So that encodes the entire hyper-Kahler structure. And then from that, one can extract anything one wants just by matrix multiplication. So, the metric is given by this. The complex structures are some other matrix product. Okay, yeah. And then I should mention, so Gautam-Voronitsky, we're focused on applying this formalism to 4D n equals 2 field theories. So you have some non-compact hyper-Kahler manifolds. We pointed out this applies to K3. The only interesting change really is that so there are two types. Okay, K3 has a whole 58-dimensional moduli space, and those parameters show up in this function z gamma and this theta gamma. Namely, so when z, when gamma is a flavor charge, is valued in the global symmetry lattice, those are just mass parameters of the little string theory. They're not dynamical, and those correspond to the moduli of K3, whereas the z electric and z magnetic correspond to the coordinates on K3. So this is familiar from Seiberg-Witten theory, where the contributions to the central charge function are A and A dual plus all of the mass parameters. And then we have the same thing going on here, where when gamma is a flavor charge, those are parameters. And when gamma is a gauge charge, then these are the coordinates on the fibers of the K3 surface in the semi-flat limit. And then the point that I wanted to make was just that in the non-compact case studied by Gautam-Voronitsky, these parameters never affect the semi-flat limit of the metric, the R goes to infinity limit, whereas for K3, they sometimes they do. Namely, they can modify the elliptic fibration to a more general genus 1 fibration. So there isn't a section. But other than that, the formalism works the exact same way. All of the equations are basically unchanged. Okay, so this is just reiterating what I just said. At large R, these functions take some universal form, the semi-flat limit, and then there's some exponentially suppressed corrections that result from BPS states running around that circle. And so we've reduced the determination of a K3 metric to the enumerative problem of counting BPS states in a little string theory on a torus, which can be reformulated in terms of Gromov-Witten invariants of K3. So these are certain piecewise constant lists of integers on K3, and their discontinuities are just governed by the wall crossing formula. And as I mentioned, there's an approximation to the full metric, which one can get just by iterating the integral equation some number of times. So if you just iterate it once, you're already doing extremely well away from the singular fibers. So this formula has been known since the 90s. This just describes the first corrections from instantons before they start to interact with each other. Okay, so I've alluded to this picture a few different times, so let me just give a explicit picture here of what these BPS states in the little string theory on T2 look like. There's this nice geometric picture. So think of this as a D3 brane in F theory on K3. So this dark circle here is a D3 brane, and these here are some 7 branes. And BPS states in this configuration can just be thought of as certain string webs moving along the base. This sort of diagram is hopefully familiar to mathematicians also as a tropical description of some holomorphic curve in K3. So these numbers here, physicists would call them the charge of some string, but mathematically they're labeling what one cycle. You fatten this string up into a holomorphic curve wrapping some one cycle in the elliptic fiber over this point. And this is telling you what one cycle to wrap. And this problem is particularly nice at points in the moduli space of K3 surfaces with where the elliptic fiber is constant over the base, because the metric that one uses on the base is then flat. And so the BPS state counting problem in those limits is just a nice combinatorial flat surface problem. Okay, so the K3 metrics, the metric on this K3 surface is singular, but one can use these invariants defined on these from this flat surface problem to get smooth K3 metrics by turning turning on these parameters. So these are the ones that affect the F theory limit, whereas these ones don't affect the F theory limit. And so what we'll do in this talk is we'll focus on a special case of this formalism where these guys are tuned to a certain limit, but one still has a whole bunch of moduli of the K3 surface to play with from these guys. And in fact, we'll focus on an even more special limit. The fiber complex structure won't just be constant, but our total K3 surface in this F3 picture will be this orbifold. So we'll think about it as a T2 fibration. F is for fiber, T2 fiber fibration over T2 base mod ZQ. So the in the Z2 compactification, you get 4 I0 star singular fibers. In the Z3 orbifold, you get 3 IV star singular fibers, and then here you have 2 III star singular fibers plus 1 I0 star singular fiber, and so on. If you look at the intersection matrix defining those singular fibers, that tells you the global symmetry of the little string theory. So here you have physically you have 4 different stacks of 7 branes, which if you probe them with a D3 brane, then at low energies it'll look like SU2 and F equals 4, the 4-dimensional SU2 and F equals 4 CFT. Or if you probe these singular fibers, then locally near each singular fiber you get one of the E6 Minahan-Nemeshansky CFTs. Here you get one of the E7 CFTs, etc. And here I'll use this throughout my talk, kappa Q. These 2 columns are just telling you that the complex structure of these 2 tori are arbitrary for the Z2 orbifold, but T2, these tori only have these Z3, Z4, Z6 automorphisms for these special values of tau. Okay, and then these last abelian groups are just because we know that the gauge symmetry of F theory on K3 is 20-dimensional, and so rank 20, and so the part of the rank not included by this non-abelian gauge symmetry has to just be made up by some abelian gauge symmetry. And there's a very nice geometric picture for what that abelian symmetry is doing. So this is the Q equals 2 description of this orbifold. So I'm just drawing the base, and the stars are the singular fibers. And because we have a Z2 orbifold, only let's say the left half of this picture is actually physical, and the right half is the Z2 image. So here is my D3 brane probing this compactification, and then string webs they can branch about and end on multiple singular fibers, And furthermore, because the base is compact, they can wind around any number of times before ending on some singular fibers. And what those abelian symmetries describe is the conserved charges associated to those abelian symmetries is just the winding number about the various cycles. Yeah, okay. So I should emphasize that as part of the spectrum of this little string theory, one will have some very simple string webs, which are just straight lines that start here and end on one of the singular fibers. And those are the BPS states which exist in the CFT limits where you zoom in near one of the singular fibers and take a low energy limit. So you ignore all of the other singular fibers. But then there are much more complicated string webs in the little string theory that don't exist in the CFT also. So we're going to do some perturbation theory soon. And at the leading order to which we work so far, we're only going to see these CFT strings, these simplest strings. We're not going to see these more complicated ones. But once we go to higher orders, then we expect to see be able to count all of these different types of string webs. But already we'll see this interesting fact where we get a whole bunch of towers of these CFT spectra, because I can end on this singular fiber, this one, I can wind around some number of times before ending. And so you get a whole infinite tower of copies of these CFT BPS spectra, which are subspectra of the little string theory spectra. Okay, so yeah, so okay, this is just emphasizing what I was saying before, that even though we're studying some orbifold in F theory, we're going to turn on those real mass parameters in order to study smooth K3 surfaces. So our counting problem involves nice flat things, but nevertheless, we're going to get smooth, interesting K3 metrics. Okay, so if you just sum up all of the contributions to the holomorphic symplectic form to this first approximation where we just iterated the integral equation once, coming from strings which look like they're geometrically m copies of a single primitive charge, then you get this formula. This is the combination that will look that BPS states contribute in. Okay, and in fact, there are some further simplifications because, like I said, at the order we're going to work soon, we're only going to see the simplest string webs, and their winding charge is also m times some basic winding charge, because the strings are literally just m copies of a single string, and so this formula simplifies a little more. So the punchline of this slide is just that this function is the combination in which BPS states are going to contribute to the metric. And okay, so now I can.
Can you remind me again which part of this formula was known before? Like you said, that people have known like the leading term.
Yeah. So this is just the Aguri-Vafa formula, where we just include the contribution from a BPS state associated to all of these simplest string webs. But if one wants to go beyond the Aguri-Vafa formula, then one can just iterate the integral equation more. This is.
So my question is whether you're already reproducing some K3 matrix formula that had been known before, like not from physics, not from Aguri-Vafa, but earlier, or not, or everything is new.
I mean, this is similar to an approximation that was studied by Gross and Wilson, where what they did was they said, let's study some approximately Ricci-flat Kahler metric, which is basically you take the semi-flat metric and you take the Gromov-Witten metrics near all the singular fibers and you glue them together via partition of unity. And then you show that there's an actually Ricci-flat metric that's close to this Kahler metric you started with. So that was done in the math literature.
But it doesn't sound that clean, like in terms of correspondence with what you're doing right now.
Yeah, exactly. And in particular, they were focused on I0 singular fibers. Whereas here, the local description is much more complicated because you have all of these mutually non-local BPS states in these CFT BPS spectra. Yeah, they interact in complicated ways. Yeah, so if one wanted, what one could do, but I don't think this has been done yet. I've actually been talking to some mathematicians about this, is study a gluing problem where one glues in some moduli space, some Hitchin moduli space in one of the corners of a K3 surface, so you start with this metric that's you do the same thing Grossen-Wilson did. But instead of your local model metric being the Gromov-Witten metric, it's some Higgs bundle metric, and then you can do the same thing. But that hasn't been done yet. I think Foscolo has done a similar thing for a different type of configuration where the local model metric was ALF, not ALG, like these guys. Okay, so now I can say something of interest, hopefully, to mathematicians, namely that already in these K3 metrics, we're gonna study from the Higgs branch point of view these CFT BPS spectra are encoded in this form of these metrics, and the charges here that are labeling the flavor charges of these BPS states are valued in the weight lattice of the corresponding singular fiber. So if I have strings which are ending on some I0 star singular fiber, so the weight lattice will then be the D4 weight lattice. So we're going to get these funny combinations of characters of representations of D4 evaluated at various points, due to multi-cover nonsense, and weighted by these integers here, which are the open string Gromov-Witten invariants. So there's some cool enumerative and representation theoretic content encoded in K3 metrics. And so far, again, this is just the CFT spectra. So this is just the simplest BPS states, but then more generally, this will continue to hold for all the more complicated string webs also. One thing that's nice about these CFT spectra is they don't wall cross compared to the little string theory spectrum that does wall cross. So I just need to give you a single list of integers for each representation of E6, E7, E8, or D4, depending on which singular fiber we're talking about. Okay, so that's everything I have to say for now about the Coulomb branch construction. So before I move on, are there any questions about that? Okay, so let me move on to the Higgs branch construction then. So this is the I guess the workhorse. This is the side where everything is completely explicit, and so we can.
I just have one question. Sorry to interrupt you. You said that something doesn't wall cross. What and why?
Yeah, good. Okay, let me say more about that. So I can get a CFT by taking my D3 brane, sitting near one of the singular fibers and reducing that to low energy, so I only see the local geometry near that singular fiber. And the BPS spectrum of that CFT doesn't wall cross. And the reason for that is, so scale invariance tells you that the spectrum can't wall cross as a function of how far you are from the singular fiber. And then a U1R symmetry tells you that you also can't depend on the angle at which you sit. So for
No, the singular fibers.
Sorry, the audio, I didn't hear any of that.
Because you zoomed in, there's no wall cross, nothing can trigger any kind of wall crossing. There no, like
Exactly.
nothing can happen.
Exactly. So yeah, so that logic fails for higher rank CFTs because you still only have a U1R symmetry. So you can't depend on the radius, how far from the origin you are, but now there's a whole sphere of angles, not just one. Okay, okay, now we're going to study a totally different construction of K3 metrics, where K3 is now going to arise as the Higgs branch of some physical theory rather than a Coulomb branch like it did before. And because of that, there's a non-renormalization theorem and there are no quantum corrections. So the setup will just be a D2 brane probing a T4 mod ZQ orbifold. And in particular, this is going to be a perturbative string vacuum. So what I mean by that is there are two different things one can mean by an orbifold in type 2A string theory, depending on some choice of discrete B field on the collapsed 2 cycles of the orbifold. One is just the straightforward dimensional reduction of M theory on that orbifold, and that has non-abelian gauge symmetry. And so I would call that a non-perturbative type 2A string vacuum because you get massless gauge bosons coming from D branes wrapping the singular 2 cycles in that K3 surface. But then there's another choice of this discrete B field, which is what we usually call an orbifold in perturbative string theory, where the gauge symmetry is just broken to its abelian subgroup. So you just have for this compactification, it would be, I guess, U1 to the 26, maybe. Let's see. 24. Okay, so that's the vacuum we'll be choosing is what one normally calls an orbifold in perturbative string theory. There's a So you might wonder then if this is not just the straightforward dimensional reduction of M theory on this orbifold, we turn on some funny discrete B field, then how do we know that we're going to get the same moduli space as we would have had we not turned on the discrete B field? But there's again a non-renormalization theorem that tells you that this choice can't matter. And so we can use this perturbative string vacuum in order to describe the moduli space of in the limit where the M theory circle decompactifies, then we just recover the M2 brane probing K3 that we had before. And so that tells you that this D2 brane moduli space will be the same as the moduli space we were studying over here in this formalism. And this is reminiscent of mirror symmetry. We have two different 3D theories. One is this little string theory compactified on T3, where we're studying its Coulomb branch. And one is this D2 brane probing this K3 orbifold, and we're studying its Higgs branch. And furthermore, the global symmetries of those two theories differ. Here we see this whole non-abelian global symmetry associated to all the singular fibers in F theory, whereas here we're just seeing its maximal torus because of the discrete B field broke it down. And yet, nevertheless, their moduli spaces agree. So that ought to sound very similar to 3D mirror symmetry, and that's not an accident. This same picture that we're using here can be used to yield the simplest mirror pairs that were studied by Trilogator and Seiberg in the original 3D mirror paper. Okay, so let me review the hyper-Kahler quotient formalism. so the idea is that in a general for 3D n equals 4 gauge theory is that one has some chiral multiplet phi in the vector multiplet whose vev vanishes on the Higgs branch, which is what one is interested in, and the superpotential is just of this form. So here mu plus is the complex moment map. It's just a function of the hypermultiplet fields, and the F term equation is just mu plus equals 0. And then analogously, you have a real moment map, which are the D terms, and they tell you the, so you have some Hermitian moment map, mu r equals 0. And the Higgs branch is then the quotient of the 0 of the potential. So you just set the moment maps to 0, and then you quotient that space by the gauge group. Okay, so this can all be described mathematically, not just physically, where you start with some bigger hyper-Kahler space, you study the 0 of some moment maps, and then quotient by the gauge group, and that gives you some hyper-Kahler quotient. So just as a warm-up for what sort of gauge theory one ought to use in order to obtain a the moduli space one desires, let's first just study the Higgs branch of n parallel D2 branes. The moduli space of these D2 branes, the transverse directions to them are, I guess, R7. And then furthermore, there's an SM theory circle. So there's an extra S1. And then the moduli space will involve a quotient by the symmetric group because the ND2 branes are all the same. So one really expects the moduli space here to be sim n of R7 times S1. But one can focus on, one can sort of arbitrarily focus only on a sim n C2 part of that moduli space just by focusing on the part of the moduli space where the vector multiplet scalars vanish, and one just looks at the hypermultiplet scalars. So when one does that, one finds these moment maps. And then a simple argument tells you that indeed the hyper-Kahler quotient with these moment maps gives you sim n C2. Here, this tells you you can simultaneously unitarily upper triangulize them, and then this tells you that they're actually diagonal. So you just get the eigenvalues of some U of n matrices. Okay, so now I want to review the formalism for studying D-branes probing orbifolds. In the physics literature, this was worked out by Douglas and Moore. In the math literature, this paper was translating the work of Cronheimer from the math literature. The idea is that you start with 2 D-branes on the covering space, on the C2 covering space, and then you just impose certain projections on all of the fields in the world volume gauge theory of those D2 branes associated to that Z2 projection. So we're going to start with some U of 2 gauge theory describing D-branes on C2, and then we require our chiral multiplets U and V to satisfy these Z2 equivariance conditions. And similarly, we're only going to consider gauge transformations, U of 2 gauge transformations, which satisfy this constraint here. Sigma Z, there's nothing special about sigma Z. It could be, the natural thing to think of it is actually sigma X, because we're just permuting the D-brane indices. Mathematically, this is just the image of the non-trivial element of Z2 in the regular representation of Z2. But okay, fine. So you just write down the most general Oh yeah, but sorry. But the point is, sigma z is computationally a bit nicer, and sigma z and sigma x are just related by a change of basis. So we prefer to work with sigma z. Okay, so one then writes down the most general solutions of these Z2 constraints. And okay, this e to the I theta, because all of our fields are in the adjoint representation, doesn't affect anything. So really one just has a U1 gauge theory, parameterized by this alpha. So the setting the complex moment map to 0 tells you these two vectors are proportional. The real moment map tells you that this constant proportionality has norm 1. And then quotienting by the gauge symmetry lets you set that constant to be equal to 1. And then there's some further gauge symmetry generated by a Z2 subgroup, which preserves this condition lambda equals 1. And so you have to further quotient by that. And that tells you that U and V are well-defined mod Z2. So indeed, one gets this C2 mod Z2 moduli space that one wanted. Okay, so now we're gonna study the T4 using the exact same formalism. So again, one starts now with some. So the idea now is you have a whole lattice of image D2 branes corresponding to the points of Z4. And then
Max, sorry, just help me out with one thing before we go in here. The relation to 3D mirror symmetry, one should be able to understand it directly from M theory on K3, which is your orbital fold, as some kind of different ways of going to type 2 string theory. Can you remind me how this works in this case?
Yeah, absolutely. So okay, one is if you take theory on K3 and you introduce an extra transverse circle and you compactify on that circle, that gives you this type 2A vacuum.
The Higgs branch we're talking about.
Yep. Mm-hmm. Alternatively, if you take K3 to be let's say T4 mod Z2, and you squish down one of the circles to be really small, then you get a type 2A T3 mod Z2 oriental fold.
I see, and somehow.
And the M2 brane probing that becomes a D2 brane probing that. And then T-dualizing 3 times gives us the type 1 D5 brane wrapping T3 that we had before.
All right, great, thank you.
No problem.
Let's go back down to our infinite dimensional quotient.
Yeah, so now we're gonna okay, so maybe mathematicians are cringing when they see this, but this is just some the unitary group on some Hilbert space indexed with a basis indexed by z to the 4, and then one just imposes.
This isn't that exotic, right? Here you're just adding infinitely many images, so one can as to compactify. So I think that this they would understand.
Yeah, exactly. This is okay. The notation is maybe going to make people cringe, but this is not hard to make rigorous. Yeah, so one just imposes these z to the 4 equivariance conditions, where again you just okay. And the result of all of that is the gauge group one has now is just maps from the dual torus to U of 1. So we thought we were talking about a 3D gauge theory with some infinite dimensional gauge group, but that's the same, it turns out, as some 7-dimensional gauge theory, where our gauge group is just U1. And our 7-dimensional gauge theory is wrapping the dual torus. That can be understood just from T-duality, because a D2 brane probing T4 becomes a D6 brane wrapping the dual torus. U and V, here from this formalism, they look like some big infinite dimensional matrices, but there's a very natural way to package those matrix elements into a U1 connection on the dual torus. So here I'm using complex coordinates, on the dual torus, psi1 and psi2, and E of n just is the Fourier Fourier component with momentum n. So in real coordinates, maybe it's a little nicer. It's just in dot y, where y are my real coordinates on the dual torus. So this is all. This is like highly non-exotic at this point. This is just a U1 gauge theory, and B is some U1 connection on the dual torus. And then the moment map equations are extremely nice. If you write down all three of them, then taken together, they just tell you that the curvature of that connection, the field strength is anti-self-dual. Yeah, one way to, said another way, the self-dual part of F vanishes, and that is exactly three equations, because the space of self-dual two forms on T4 is three-dimensional. And so we're just looking at the moduli space of anti-self-dual connections on this dual torus mod gauge equivalence. And because we're dealing with a trivial principal bundle, we're actually being anti-self-dual is the same as being flat. And so we're just looking at the moduli space of Wilson lines on the dual torus. And that is indeed T4, the original torus. So this does in fact give a very highfalutin way to construct T4 as an infinite dimensional hyper-Kahler quotient. And it's physically sensible that we get a compact moduli space, because those are just large gauge transformations. Okay, so now let me finally get to K3. These ideas were actually studied back in the 90s. Oops. So the idea is just to start with the U of Q gauge theory on the dual torus that I introduced in the last slide, and then just impose some ZQ equivariance conditions. So iota here is just the action of ZQ on the dual torus, and the moment maps, but because of those projections, one now can, it turns out that these terms are gauge invariant. So here, y prime indexes the fixed points of the dual torus, these terms here are just valued in the in the Cartan subalgebra of the Lie algebra associated via the Mackay correspondence to the singularity on the dual torus. So instead of telling you the self-dual part of F is 0, it's just the self-dual part is 0 everywhere except for at the fixed points where it's singular. So we're just looking at the moduli space of these singular ZQ equivariant anti-self-dual connections. But again, this is just some hyper-Kahler quotient of some infinite dimensional flat space, which is parameterized by the Fourier components of the connection by the group of ZQ equivariant SUQ gauge transformations, which preserve these singular boundary conditions. And so you can count how many parameters there are here. So as I mentioned before, there are three self-dual two forms on a torus. Self-dual constant coefficient harmonic two forms on a torus, and so you get the parameters here come in triples, which makes sense because there are three moment maps, and then the if you just count how many fixed points there are and how many and what dimension the Cartan is, then you get you find the that you get 58 moduli in this construction, and that's exactly the dimension of the moduli space of K3 surfaces. So we expect that by changing these parameters as well as the moduli of the torus that you're orbifolding, then you can cover the entire moduli space of K3 surfaces.
Can you see again, can you explain again, how do you see that this is how the block parameters enter?
Yeah. So the, okay, one way is, okay, let me say it this way. We're familiar in gauge theories with Fi parameters being valued in the associated to U1 factors in the gauge group, but more generally, they're not valued in the Lie algebra. They're valued in the Lie coalgebra, the dual of the Lie algebra, and you can see that just from the fact that the way that they show up in the Lagrangian is, you take the Cartan pairing of the Cartan killing pairing of an Fi parameter with some field in the adjoint representation, and so so they should really be showing up in the dual space to the Lie algebra, and so the right words to say are then that this should be some co-central factor in the Lie coalgebra and of your gauge group, and that turns out to be parametrized by this. So you can show that these are gauge invariant because of the ZQ equivariance conditions. So the ZQ equivariance conditions at the fixed points on the dual torus is precisely the statement that you commute with these matrices, and so gauge transformations preserve this term.
Can you somehow say that if I were to blow up the singularities, that then this reduces to what you would know on a smooth space, or you
yeah.
can't?
So what I can say is, if you study, we're about to, I'm about to write this formalism in terms of the Fourier components, because then everything looks like some nice infinite dimensional linear algebra, and the zero mode of that construction will then exactly look like the ALE hyper-Kahler quotient of Kronheimer that you locally get near the zero fixed point.
Thank you.
So that's an intuitive way to understand why those are the right Fi parameters. And then similarly, yeah, for the Q not equals 2 cases, the counts of these Fi parameters works a little bit differently, but it ends up working out. In particular, there's a subtlety here for Q equals 4 and 6, namely so for Q equals 2 and 3, all of the fixed points just have ZQ stabilizers. But for 4 and 6, some of them have smaller stabilizers, and so they get identified with each other. And so then you get relations between these Fi parameters associated with points that get identified. But when you account for all of that, then the counting works. And so we expect this will cover the entire moduli space of K3 surfaces. But then when these parameters are small, there's a particularly nice perturbative description. And so, yeah, just zooming out a bit, for every possible torus orbifold of K3, we're just focusing on ZQ orbifolds for simplicity here, but it works the same for the non-abelian orbifolds also. You get a construction of this sort that presumably covers the entire moduli space of K3 surfaces, but then in the limit where the Fi parameters are small, so near the corresponding orbifold limit, there's a nice perturbative description of the solution of these moment map equations in some nice gauge. Okay, so just as the first point, I promised that I would yeah. So the zeroth order part of perturbation theory should then be that when the Fi parameters vanish, we just get the orbifold, and we can see that very explicitly. So the zero mode. So again, we're just dealing with flat U of Q connections because this term isn't here. So we're just dealing with the Wilson lines, and then the zero mode moment maps and gauge transformations allow us to further restrict the zero modes to be of this form. Yeah, this is exactly the ALE hyper-Kahler quotient. Yeah, and then the very last step is that there are some extra gauge transformations because of this in this infinite dimensional gauge group that preserve all of these that preserve this gauge choice, and so we have to further quotient by them. And what they do is they implement the z to the 4 quotient, so you get T4 mod ZQ, not just C2 mod ZQ. So here n labels my lattice vectors in z to the 4, and nu and nv are just complex coordinates for those lattice points. And okay, the reason they're called quasi-large, not large, is because they're actually they can be. There's this funny thing with infinite dimensional gauge groups where you can be in the connected component of the identity, but still not in the image of the exponential map applied to the Lie algebra. And so we call those quasi-large. Okay, so now I can describe our perturbation theory. Namely, we're going to parameterize the zero modes of our connection in this way. So U orb is the formulas from the last slide, and then these deltas will just be some orthogonal pieces in the zero modes. So we're going to write the most general solution of the orbifold constraints on the zero mode in this form. And then the point is that U and V, which show up in this orbifold, U orb and V orb, are just going to be our coordinates on the K3 surface. So we'll solve for some embedding of K3 in a particular gauge into that infinite dimensional flat space. So we'll solve for all of the values of the nth Fourier modes of our connection as a function of the pieces of the zero modes U orb and V orb. Okay, I should, yeah, is that clear, the starting point? Okay. So the idea then is, suppose inductively that you know the nu minus 1th order approximations, then write the nth order approximation as the nu minus 1th plus some change. And then if you write the moment map equations and keep only the order nu terms, then they're linear in these changes, even though the full moment maps are nonlinear. And furthermore, the full moment maps couple all of the different Fourier modes together. But at this order where you're only keeping linear contributions in the nth order terms, the moment map equations just decouple into finite size chunks. And so we're just doing finite dimensional linear algebra. And similarly, there's a natural gauge choice which shares those features. So this is like a non-abelian analog of Coulomb gauge. And okay, so very explicitly, these are the linear equations that we're solving at the nth order. And we just solve these for every n. So this is the complex moment map, this is the real moment map, and this is the gauge fixing condition. All of the magic then is encoded in the construction of these constants over here, which are constructed from the lower order terms that you've already found. And notice that the equations on the right-hand side are the exact same for all values of nu. The coefficients on the right side are the same. And so, if you're gonna think of this as, if you're gonna solve these linear equations by inverting some matrix and then multiplying this vector of constants, then the matrix you're inverting is the exact same for every value of nu. the only place that it matters which nu you're at is the vector of constants over here. So very explicitly, for nu equals 1, those constants are just the fi parameters that we started with. I called them eta over there, but you rearrange them in certain linear combinations to change notation, and then you get x's. And then for nu greater than 1, you just construct those effective fi parameters from the lower order terms that you've already found. Okay, so I just solved this linear equation. Okay, I don't want to spend time describing all this notation, but the point of this slide is it's extremely explicit, and you can plug this into Mathematica very easily. This is just some finite sums, so this is very computationally very useful. You can just plug this onto a computer, okay, so there's this cool fact about this solution, which is if you sum up the contribution from each nu in order to find the complete non-perturbative solution, then you learn that then you obtain this equation. And if you squint your eyes for a little bit, you'll realize that this is an integral equation on the dual torus. I just wrote it in momentum space because I've been working with the Fourier components. But this is I think we're basically convolving these delta u and delta v with some Green's function. That's what's going on down here. And here we're convolving it with some distribution of delta functions. Okay, times the fi parameters. So I think, so Arnav and I are planning on making all of this rigorous in the near future, and this should be the basis for doing so. Namely, you just apply the Banach contraction principle to these integral equations, and show that iterating them ad infinitum gives you a solution to the moment map equations in this gauge. So this is again extremely explicit, and this is in the Coulomb branch formalism. You had to deal with these integrals over infinitely many rays in the complex plane, one for each BPS state that was showing up, whereas here you're just doing a single integral over the dual torus. So it's formally this, there's some formal similarities between the Higgs and Coulomb constructions, but in the details they differ in some interesting ways. So yeah, it's actually, one question is, yeah, it would be interesting to understand the relationship between these two constructions better. Okay, anyways, so now that one has these embeddings of K3 into the infinite dimensional flat space, then the hyper-Kahler quotient construction immediately gives us the Kahler forms on K3. You just pull back the Kahler forms from that flat space. So concretely, you have this function un as a function of u and v, and you just construct it. Yeah, you just plug this into there, and then you get some two forms on K3. Okay, so now I'm going to describe what happens if you do this explicitly at first order in perturbation theory. So here's the orbifold limit, where if you just plug in 0 fi parameters, then you get these familiar flat Kahler forms on just a torus, or here really the torus orbifold. And then we're going to add the first order perturbative corrections. And they take this form. So again, I don't want to unpackage all the notation, but you can see this is very explicit and very simple. And given those matrices, those Kahler forms, we plug them into Mathematica, and indeed we found that the metric is Ricci-flat, the complex structure is all square to -1, ij equals k, etc. So all of the identities from hyper-Kahler geometry work exactly. So that was pretty satisfying. Okay, so now I'm going to compare the Higgs and Coulomb formalisms with each other. So before I do that, are there any questions about the Higgs branch approach? Okay, cool. So the idea now is we're going to use the Poisson resummation identity. Motivated by the SYZ conjecture, we're going to only Poisson resum over. So remember, here we were dealing with sums over a 4-dimensional lattice, z to the 4. But motivated by the SYZ picture, that's supposed to be underlying this Coulomb branch formalism, we're just going to Poisson resum over a 2-dimensional lattice associated to the fibers of this orbifold. So we won't Poisson resum over the lattice that's associated to T2 base, just the lattice associated to the T2 fiber.
So we are doing T duality on T2.
Yeah, exactly. Okay, furthermore, as I mentioned before, we'll tune the complex FI parameters to 0, so we'll only have the real FI parameters. And the reason for that is going back to this formalism, what that translates to is the F theory limit is an orbifold limit, and we're only smoothing things out as we go from F theory to M theory. So the BPS state counting problem we're dealing with is still on the orbifold, so the counts of string webs on some nice flat orbifold are going to give us smooth K3 metrics, because we're using the real FI parameters to resolve the orbifold, not the complex ones.
Sorry, I didn't understand. The metric you got on the previous slide is smooth.
Yeah, that's right. My point is the reason it's smooth is because we turn on FI parameters. If we didn't have any FI parameters on, then it would be singular. So I'm just saying we're going to turn on only the real guys, so it'll still be smooth because of that. But the F theory orbifolds whose BPS state counting problem we're trying to solve, that will just be a flat orbifold.
Because it only sees the complex structure or something.
Exactly, but yeah, the way to think about that is that the complex FI parameters are holonomies for some background gauge field in the little string theory as you compactify on T2, whereas the real FI parameter is some extra holonomy you get to turn on once you compactify on the third circle. So the PPS state counting problem only cares about the little string theory on T2, so it only sees these guys. Okay, so the result of doing this Poisson resummation is of this form, which, if we compare with this, but you'll hopefully see they're the same. And there's just some function here, f. So I'll explain what that function looks like in a second, but first let me just mention the geometry of those string webs is encoded in this lattice of winding charges here. So we can explicitly see the geometry of string webs winding around the base some number of times before they end on a singular fiber. That's what this lattice is. And that's very explicit here in the form of the dependence of the central charge. It takes this form. So this is basically the tension of one of this string. It's just the magnetic charge times the complex structure.
I think you're showing some things that, at least on my screen, don't actually show up. I mean, I see the forms for the two forms, but I don't see the tension. It's just not there.
Do you see this thing I just highlighted or no? Oh, weird. That's interesting. I mean, it says I'm screen sharing.
If you restart the screen sharing, that's probably help.
Yeah, okay, let me do that. Can you see this now? It just looks blank, or?
It shows what was before you opened the sharing. Yeah, it somehow shows only part of your presentation. That's.
What you should do, you should send us the slides and we'll post them and we can, you know, review them later on. Maybe.
Okay, that sounds good. Okay, yeah, sorry about that. That's weird. I don't know what is causing that. Oh, you know what I can do? Z. Uh-oh, all right. It's like trying to be too smart. Okay, you can see that, right? Okay, great. So yeah, the point is just that there's this factor here which tells you the tension of those strings, which is, you know, just the electric and magnetic charges, and then the length of the string. So this is the coordinate labeling where on the base of the K3 surface the D3 brane is, and A naught here is telling you which singular fiber the string ends on. So the you know, the geometry of those string webs is encoded in this way, in this formalism. Okay, and then furthermore, these functions f, because at this order in perturbation theory that we're working on, we only see these simplest string webs. Then we're only, it turns out, yeah, so we're only seeing these towers of CFT spectra, and so the only dependence on this winding charge is just what type of singular fiber the string ends on, and so it doesn't care about how many times you wound around before you end on that singular fiber. So I can just label these functions, instead of by their winding charge, I'll just label them by the stabilizer of that singular fiber. So, you know, in T2 base mod ZQ, each singular fiber corresponds to one of the fixed points of that ZQ action. So I'll just label the singular fibers by their ZQ stabilizer. If I have a Z2 stabilizer, that just corresponds to an I naught star singular fiber, or physically, you know, the BPS spectrum is that of the SU2 and F equals 4 CFT. Then you get this function where you have four four different FI parameters, which I'm parameterizing in this way, which corresponds to the fact that the rank of spin 8 is 4. Similarly here, for a Z3 singular fiber, you get, this corresponds to an E6 Minahan-Nemeshansky theory, and indeed you get 6 FI parameters, because you have 3 of these, but they're complex. Then for the E7 theory, that has a Z4 stabilizer, you get 4 parameters, because here there are 2 of these, but they're complex. And then interestingly, the Z4 function is built out of the Z2 function. And I'll explain in a second. That's not just a coincidence. Yeah, but first let me just state the answer. So you take the Z2 function, which, remember, depended on 4 variables, because spin 8 is 4-dimensional, or rank 4, and you specialize these 2 variables equal to each other, and that gives you so then you have 7 variables in total. And the reason that you specialize these 2 equal to each other is what I mentioned before, that some of the singular fibers only have Z2 stabilizers, and so you have to identify the FI parameters that you would naively associate to those 2 different points. So that's what's going on here. And then similarly, the E8 theory has a Z6 stabilizer, and you build that out of these 3 different functions, where again you specialize certain parameters equal to each other. Okay, so why did we get formulas that look like this, where these E7 and E8 guys are built out of the functions associated to the other stabilizers? The point is that way that this Poisson resummation works is that you get certain terms that contribute to all singular fibers, and then you get certain terms which only contribute to singular fibers. So this gives you relationships between the different singular fibers that show up in the same F-theory compactification. So if I have the Q equals 4 F-theory compactification, then I have both SU2NF equals 4 singular fibers and E7 Minahan-Nemeshansky singular fibers. And so this tells me that the BPS spectra of those two theories have to be related to each other, which is a very cool unexpected result. So far we're only working at first order and perturbation theory, but in light of how this hyper-Kahler quotient formalism produced those relationships, we conjectured these all orders exact relationships. And then with the available data, we tested this, and they actually seem to be satisfied. So this is sort of amazing because the spectra of the SU2NF equals 4 theory couldn't be simpler. I'll review it on the next slide, but you know, only the 8-dimensional spin 8 representations and the singlet spin 8 representations contribute. Furthermore, the only supersymmetry representations that show up are vectors and hypers. So this has a very simple spectrum. Whereas in contrast, the Minahan-Nemeshansky BPS spectra are really complicated. And yet, if you package them in this way, in these functions, you take these linear combinations of characters, Taylor expand them. Well, sorry, you don't even have to Taylor expand them now because, like I said, this is supposed to hold at all orders. So yeah, you package the BPS spectra in this funny way, specialize them in this way, then they exactly agree with this specialization of the SU2NF equals 4B functions. So, you know, just as a review, the BPS spectra of the SU2NF equals 4 field theory it is just very simple.
But so at this point, right, you have a problem that's well defined on. This is still something that you're conjecturing some properties of the spectrum on the Coulomb branch side, right? Yeah.
So yeah, so we should by proceeding to all orders with our Poisson resummation, we should be able to get the exact BPS spectra, which in particular should prove this conjecture, hopefully. But for now, it's just a conjecture because right now we're just observing this at, you know, we observed that it held at leading order, then we tested it on all available data at all orders. But because, you know, Knightsky and collaborators have found a bunch of BPS states in the Minahan-Nemeshansky spectra, and so we could compare with the functions that we construct out of the data that for the available data. And in those cases, it does work to all orders. And okay, so yeah, so as I mentioned, so the BPS spectra of the Minahan-Nemeshansky theories are much more complicated. You know, you have arbitrarily large representations. The imprimitivity of gauge charges that shows up is arbitrarily large. And so the fact that this specialization of these functions works exactly with these very simple SU2NF equals 4 things where you only get 1 and 2 and you just have 8-dimensional guys or singlets. That was sort of that was very surprising. Okay, so so far at leading order, we've derived constraints on the spectra of these theories for arbitrarily large imprimitivity. So you know, this is sort of an orthogonal direction to what Knightsky et al. Have done because they have the exact BPS spectra, but for small values of imprimitivity. Whereas for arbitrarily large imprimitivity, we know that this holds, that these functions hold. But you know, this is just at first order in these parameters. And so at leading order in the F5 parameters, we have some new constraints. They're fairly weak, but they did give us some new BPS state counts. But proceeding to higher order should then yield the entire spectrum. And not just of the CFT, but again, of the full little string theory also. Motivated by these leading order expressions, we also conjectured some strong all orders relationships between the BPS spectra of the various field theories that coexist within the same F3 compactification. And then I should stress that, so you might have thought, since all of this worked out so nicely, maybe these fancier string webs just don't contribute to the metric at all. They somehow cancel out exactly. But there's a simple argument that shows that that can't be the case, just using the wall crossing formula. Namely, if I started here, then, so this string web is just a bound state of this simple string with this simple string. And so if I start here, where that bound state doesn't exist, and then I move out, the wall crossing formula tells me that this string web has to contribute to the metric. So this just means that there have to be some cool cancellations that make it so that all of these more complicated string webs don't contribute at leading order in perturbation theory, but they'll contribute at higher orders. So presumably this is, this can be explained using Fermi zero modes or something, but we haven't done that yet. Okay, so the last thing I wanted to do was to mention another Coulomb branch construction. So using a slightly different little string theory. This one can only see certain K3 surfaces, not all K3 surfaces. But the benefit of it is that it's a much simpler little string theory. And so the counting problem, one might be able to directly solve the counting problem, not just by comparing with the Higgs branch formalism like we did here. So the idea is to instead study the simplest maximally supersymmetric little string theory. One way to think of this is type 2B string theory or type 2A string theory with two parallel NS5 branes. Once you start compactifying it on a circle, they're the same, they're T-dual, so it doesn't matter if they're in 2A or 2B. Or equivalently, you can think of this as just type 2A or type 2B compactified on an A1 singularity. So that gives you the little string theory. Then we again compactify it on a 3 torus, and the moduli space is sim2 of T4. But you can now turn on, because this has 16 supercharges, not just 8 like we were dealing with before, there's a spin 4 R symmetry group. But we only really care about preserving the spin 2 R symmetry group of a generic n equals 2 theory. So we can just think of the other SU2 in that spin 4 as a global symmetry, and turn on R symmetry holonomies for that SU2 on the 1 cycles of this T3. And so those are half BPS, so they break SUSY to 3D n equals 4, but that's fine. And in fact, that gives you a more interesting hyper-Kahler moduli space rather than just sim2 T4. So okay, this is not really exact. What's really the correct statement is you get the Hilbert scheme of 2 points on T4, which is isotrivial T4 K3 fibration over T4. What that means is just it's a fibration of K3 over T4 where all of the fibers look the same. And the non-trivial monodromy in that fibration is just due to the fact that all of these fibers have some Z2 to the 4 symplectic automorphisms, and the monodromy just acts by those Z2 to the 4s as you go around the 1 cycles of the T4. But this is simple enough that you can still get the K3 metrics from this. And in particular, if you just look at the fiber over 0 in this T4, then that just is a K3 surface, and you can just look at that metric. So so there's a K3 metric embedded in the moduli space if you just kill off this T4 factor. Okay, so again, you only get certain very special K3 surfaces from this construction rather than the most general K3 surfaces. But the upside is this is, you know, this is a very nice little string theory. And in particular, if we only remember we don't treat the 3 cycles of this T3 on the same footing. We single out one of the circles as very special. The BPS, if we only turn on the R symmetry holonomy on that 3rd circle, but not the first 2, then the BPS state counting problem one has to solve is in the maximally supersymmetric little string theory, just compactified on T2 with no R symmetry holonomies at all. So this still, in a sense, has the flavor of an n equals of an 8 supercharge counting problem rather than a 16 supercharge counting problem, in the sense that one needs to refine by the R symmetry, but one is still in a 16 supercharge compactification. Yeah, okay, I just said this. So again, the string web picture now is extremely nice. Now it's just you have two D3 branes in type 2B string theory on T2. So now there are no singular fibers, and we're just studying string webs stretching between one D3 brane to another. So you get configurations that look like this. Mathematically, this is again just open string Gromov-Witten theory of T4 now, but you have states that end on 2 different boundaries. And more generally, the BPS states for describing a metric on Hilbert of T4 should just have n boundaries. So this is a cool modification of the usual Gross-Siebert formalism that I don't think has been studied, because in part for Calabi-Yau threefolds, this generalization is not so interesting, I think. But for hyper-Kahler manifolds, the Hilbert scheme of points gives more examples of hyper-Kahler manifolds. And so, yeah, that's cool. And then if one instead realizes this little string theory via geometric engineering, so you have you have F theory on an affine A1 singularity, by which I just mean the total space of an I2 singularity over a disk. Then if you, again, we studied the BPS state counting problem of that little string theory on T2, but F theory on T2 is just type 2A string theory, because F3 on a circle is M theory and M3 on a circle is type 2A. So the point is then we're just studying the generalized Donaldson-Thomas invariants of an affine A1 singularity times T2. So, you know, this is just a piece of the BPS spectrum of type 2A string theory on K3 times T2. So you might think we know everything about it. But again, the point is that we have to refine by some R symmetry of this little string theory, and that doesn't exist in K3 times T2. It only exists in this non-compact setup. So far, this is not known. But we're very hopeful that ideas from Malik and Oblomkov can be generalized to study this problem. Again, one can't just study the normal Donaldson-Thomas invariants. One needs the generalized ones that one needs to study this at arbitrary points in moduli space, not just the particular chamber that Malik and Oblomkov study. Yeah. This seems like a potentially promising way to directly solve this counting problem. Okay, so in conclusion, this Higgs branch hyper-Kahler quotient formalism yields computationally useful explicit analytic expressions for K3, and they secretly encode the solution to this little string theory BPS state counting problem, where by secretly I mean via Poisson resummation. So there's this cool enumerative and representation theoretic information hiding inside of K3 metrics. And we similarly also find this interesting dependence of the metric on the geometry of these string webs. And via string dualities, we can recast this BPS state counting problem in terms of open string reduced Gromov-Witten theory, which aligns with the SYZ conjecture. And then but once we find the full BPS spectrum of the little string theory, which we should be able to do by comparing with the Higgs branch picture, then we'll get a second equivalent construction of K3 metrics, which again has a small expansion parameter, namely the distance from the semi-flat limit. And so that's again computationally useful. And there are other approaches one might use for directly attacking this counting problem. So I mentioned geometric engineering and these string webs, which are probably I think the two most promising. In particular, those are promising in this n equals 1, 1 little string theory. Yeah, and there are some neat connections with open topological string theory. Here, the idea is just it's a real version of Noether-Lefschetz theory, where if you're interested in the open string Gromov-Witten theory of K3, you can attack that by studying K3 fibered threefolds and study the open string Gromov-Witten theory of those threefolds instead. So that was studied by Chikati, Naitsky, Vafa, and in the math literature by Yushen Lin. So that's an interesting question, because instead of studying metrics of some moduli space, one's studying the superpotential, which can be computed via open topological string theory. And then even without most of the BPS counts,
Max, I didn't understand the last thing, and I should have been able to understand it. Can you just repeat just the last couple of sentences? I didn't follow really.
Yeah, let me say it.
How do you relate the metric computation to superpotential?
Yeah, so the idea is so remember we're interested in the open string Gromov-Witten theory of K3. Let's instead study a K3 fibered threefold. Well, then and study a D3 brane, which is wrapping an elliptic fiber of K3 as well as a one cycle in the base. So then the BPS the opens so
in the threefold, this brane is two-dimensional or three-dimensional? It's three-dimensional.
Yeah. Okay. So it's wrapping a special Lagrangian. So now we have holomorphic disk instantons, which contribute to the superpotential of this D3 brane. A subset of those holomorphic disk instantons will be the instantons that we care about that just live in the K3 fiber. Yeah, exactly. So in a sense, the Calabi-Yau picture is actually harder because you're going to get extra disk instantons that don't just live in the fiber. But a subset of that spectrum of the states that contribute to the superpotential will be the states of interest that contribute to the metric. So yeah, so actually, one idea we're quite excited about is this same Higgs branch approach applied, instead of applying it to T4 mod Z cube, one can apply it to say T6 mod Z2 squared. And then if one inserts a D-brane wrapping some cycle there, then one via the same non-renormalization theorem reasoning, one should be able to compute the open string, the superpotential of that D-brane. So now the metric on that moduli space won't be protected, but the superpotential will be protected. And so this same Higgs branch approach ought to allow one to compute open string Gromov-Witten invariants of threefolds. that have torus orbifold limits. So that is something, yeah, that I think would be a very, very cool generalization of these ideas that we want to pursue at some point. Yeah, actually, that idea is motivated by something I talked with you about a while ago, where we're you know, if you, in general, you can't t-dualize the base of a fibration because that direction isn't an isometry of the compactification, because the fibers are varying over the base. But for the case of a torus orbifold, we do know how to t-dualize the base, and you just exchange the orders of orbifolding and t-dualizing, and so okay, yeah, so one can replace this D3 brane wrapping some special Lagrangian in the orbifold by a D0 brane just probing the space, I'm okay. I mean that's just mirror symmetry for this orbifold, but yeah, that's so yeah, that I think should give a useful way to solve the open string Gromov-Witten theory of certain resolved orbifolds. Okay, and then more generalizations are, so I told you how to get metrics on K3 via a hyper-Kahler quotient. We actually think we can probably get at least Hilbert schemes of points on K3 and T4. So that's almost all known compact hyper-Kahler manifolds. The idea is if one, instead of just having a D2 brane probing a torus orbifold, one also inserts D6 branes wrapping the torus orbifold, then one can get Hilbert schemes of points via that construction. Like if I have n D2 branes probing K3 or T4, the moduli space is just sim n of K3 or T4, but I can, if I wrap a D6 brane on that, then I get the extra Fi parameters I need to resolve that. So 3D mirror symmetry again relates that to some little string theories and some counting problems. And we also think we might be able to get O'Grady's exceptional manifolds from this, but okay, that's for later work. And Poisson resumming 1, 3, or 4 times is also possible. So, here I described just doing it twice because of our motivation with the SYZ conjecture. So it seems likely that those will yield further interesting expansions with corresponding counting problems. And although we focused on K3 and little string theories, analogous stories hold for ALG, ALH, and ALF manifolds. So, these are certain monopole, Higgs bundle or Higgs bundle moduli spaces, for example. So, okay, let me stop there.
All right, Max, let's all thanks, Max. Let's see how it is. That was somewhere. Okay. Aha, here we go. Yeah, Max, thank you for a spectacular talk. This is really amazing stuff. So I was, yeah. Let's see. I asked lots of questions, so let's do others have questions. Okay, maybe people are a little bit tired because I think we are on record. Our seminars are informal and long, but this is probably the longest, certainly among the most informal, because we had some issues with the beginning. But anyway, so more questions, anyone? Okay, well, if not, this is really a fantastic, beautiful story. So thanks, Max, for coming and for telling us about it. And we look forward to hearing more.
Thank you very much. Yeah, thanks for the invitation. This was great.
All right. Well, thanks everyone for joining, and keep safe. And okay. Bye-bye.